Welcome to the National Science and Technology Medals Foundation virtual series, where we're meeting the top minds in STEM to learn more about their paths to success. I'm Sarah Williams, a science journalist, and chatting with me today is Jennifer Dionne, an associate professor of materials science and engineering at Stanford University. Dr. Dionne has spearheaded new ways of imaging chemical reactions and biological molecules, and she has been recognized for her work on how to manipulate light in new ways. Thanks for joining me today, Dr. Dionne.
Oh, it's my pleasure. Thank you so much for taking the time to talk with me.
Maybe this is a basic question, but why is light so critical to microscopy at all?
Yeah, a great question. You could turn that around and say, why is light so critical for us being able to navigate our world? And while we can move around at night by feeling our environment, and we can get a sense of where we are and where we might be going, for many of us, being able to see the world with the lights on provides a much clearer image and much a more well-defined knowledge of our environment. So light is not the only means with which we can learn about what's happening at the molecular scale, but it's a really powerful method and one that many humans can learn a lot from.
Why is it useful to study light, and what kinds of scientific questions are there about light and how to manipulate it?
In my own experience, I tend to be a very visual learner, and I feel like a lot of the knowledge that I've learned myself and that humanity as a whole has learned has come from what we can see. And it, of course, requires light, oftentimes, to be able to directly see what's happening. But so much of the intricacies of nature and also of the engineer world depends upon what's happening at the molecular scale. And that's such a small scale where it's hard to use our eyes to see what's going on. And it's also hard to use state-of-the-art instruments to illuminate what's happening at the molecular scale or at the nanoscale. So we're interested in coming up with ways of using light and new materials to visualize what's happening at the smallest of scales, to see what's happening at the cellular level, the subcellular level, and at the molecular level. I'll also add that light is obviously an abundant and renewable resource. So it's kind of ubiquitous. I think we tend to take it for granted, but in addition to being a great way just to allow us to navigate and learn and understand our environment, it also is an incredible energy source. And the sun provides more energy to the earth in an hour than humans use in an entire year. So if we can learn to control light to allow us to better understand our world, we might also be able to utilize that light to better power the world and provide the energy we need.
So you've also worked on a lot of new imaging techniques. Why is it so useful to be able to see things at this really minuscule scale? What are some of the applications of that?
Yeah, let's think about, for example, a pandemic that's on everyone's mind, COVID. The virus that is responsible is roughly 100 nanometers in size. So it's very difficult for us to see with our eyes. It's challenging to see with existing optical microscopes. And if you want to visualize, say, the arrangement of proteins on that particular virus, you usually have to turn to electron microscopy or cryo-electron microscopy in order to understand like the spike proteins that are coming out of the virus and the antigens that are infecting the human. So we're interested in developing imaging techniques that allow us to use light to visualize, say, the proteins on the virus itself, and to actually watch it working dynamically. So in cryo-electron microscopy, you can get amazing spatial resolution, but it's very hard, if not impossible, to watch how all of the spike proteins are interacting with our immune cells, like our B cells or T cells.
Mhm.
So everything, there with the virus happening on an extremely small length scale, definitely sub 100 nanometers, all the way down to the 1 nanometer regime, potentially the sub 1 nanometer regime. We're trying to develop new imaging methods that allow us to visualize, how our immune system is interacting with the virus and follow kind of those responses in real time.
Well, it seems like a lot of these challenges you're tackling are really interdisciplinary. How do you manage straddling different fields?
Yeah, that's a great question. And I think science is becoming increasingly interdisciplinary. There certainly is value to scientists who work in a more like solidary approach and go deep into a particular topic. But in my own case, we've found that a lot of our imaging techniques can find applications both in the biomedical field and also in sustainability. So I've been lucky enough to be part of collaborative teams that bring together specialists, including doctors, clinicians, biomedical scientists, and there we're able to brainstorm back and forth how we can take some of our materials and make them more biocompatible, ensure they're not cytotoxic, and then use them for new medical imaging techniques or new therapeutics. So I try to learn as best as I can the language of our collaborators so that way we can have a really fruitful discussion. And I've benefited tremendously from the ability to work across disciplines and across schools.
Let's back up and talk about your career path because I think that might resonate with some of our student viewers as well. I read that as an undergraduate, you actually worked as an oceanography researcher. How did that lead you to where you are now?
Oh my gosh, yeah, that's a great question. Um, so I'll just start by saying I grew up in Rhode Island. So for anyone who's listening in from the East Coast, I have strong ties with the East Coast. I loved it there. My mom was a nurse and my dad was a construction worker. Um, and I really enjoyed the science classes that I took in high school. Also, really enjoyed just asking my parents lots of questions about everything from why the sky was blue to how we could see past our galaxy. I really was into astronomy at the time. And then when I went to college, um, I decided on a physics major because I thought it would give me the opportunity to learn a lot of the foundations of how the world works. But in terms of research opportunities, I was lucky enough in my junior year to have the chance to work in an oceanography lab. So to be honest, I was kind of attracted to the program by the opportunity to do outdoor field work or research cruises. As luck would have it, I wound up working again in a sub-basement laboratory, but that undergraduate research program in oceanography was my first real exposure to what it takes to do kind of frontier research. In many ways, while it was an oceanography research program, it was very interdisciplinary. My first, I guess, real research experience that taught me about the value of interdisciplinary research, and also the importance of connecting a lot of the physics principles I had learned with a really important application, in that case, in environmental sustainability.
I think a lot of students struggle with figuring out their career path, both what discipline to pursue and what particular questions to ask and whether to go into academia or not. What's your best advice for students and young scientists who are grappling with these kinds of questions?
My first piece of advice would be try your hardest to enjoy what you're doing now and just learn as much as you can. It's very hard to make predictions about the future, but I think if you excel at what you're doing in the present, you'll wind up with far more opportunities than you can even imagine in the future. um, I guess the second piece of advice is to think about when you're talking with your future hypothetical grandchildren, what do you want to tell them that you did? And how do you want to tell them you had an impact on the world? Having the ability to think, slightly longer term about what sort of impact you want to leave on the world provides kind of an internal compass that will guide you as you make decisions along the way.
I look forward to hearing what you come up with next. Thank you so much for talking today.
Yeah, thank you for taking the time.
This is the National Science and Technology Medals Foundation's STEM Spotlight Series.